When dealing with a 480 volt to 120/240 volt transformer, specifically a delta-wye configuration, understanding the grounding and bonding requirements and the secondary side, the 120/240 volt panel, is crucial for safety and proper system operation. The primary reason for bonding the neutral and ground in a 120/240 volt panel stems from the delta-wye transformer's inherent characteristics. In a delta-wye transformer, the primary side, the delta side, does not have a direct connection to ground. The neutral is established on the secondary side, the Y side, by connecting the center tap of the secondary winding to ground. This creates the 120 volts to neutral voltage on each leg and the 240 volts line to line voltage. Bonding the neutral and ground in a 120/240 volt panel is essential for several reasons. Firstly, it establishes a low impedance path for fault current to return to the source. This low impedance path is critical for the proper operation of overcurrent protection devices, such as circuit breakers and fuses. When a ground fault occurs, a large current flows through the grounding system, tripping the circuit breaker or blowing the fuse, thereby quickly de-energizing the circuit and preventing electrical shock or fire hazards. Secondly, bonding the neutral and ground prevents the neutral from floating. A floating neutral can occur when there is a break or high resistance connection in the neutral conductor. In such a situation, the voltage on the neutral can drift away from 0 volts, potentially creating a shock hazard. This is because the voltage between the neutral and ground can become significantly high, and any conductive object connected to ground could become energized. Thirdly, the bonding provides a stable reference point for the electrical system. By connecting the neutral to ground, the voltage on the neutral is maintained at or near 0 volts relative to ground. This ensures that the voltage on the other conductors in the system remains stable and predictable. Without a proper bond, voltage fluctuations can occur, which can damage equipment or cause erratic operation. The National Electrical Code (NEC) provides specific requirements for grounding and bonding electrical systems. It is important to adhere to these requirements to ensure the safety and reliability of the electrical installation. NEC Article 250 covers grounding and bonding. This article provides detailed information on the methods and materials that must be used to ground and bond electrical systems. Specifically, NEC Section 250.24 addresses grounding requirements for separately derived systems such as transformers. This section requires that the neutral of a separately derived system be grounded at the transformer and at the first disconnecting means or overcurrent device. This ensures that there is a low impedance path for fault current to return to the source. The specific method of bonding the neutral and ground in the 120/240 volt panel typically involves connecting the neutral conductor to the grounding electrode conductor at the service equipment. The grounding electrode conductor is then connected to a grounding electrode system, such as a ground rod, ground ring, or metal water pipe. This grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provides a path for fault current to dissipate. It is important to use the correct size grounding electrode conductor, as specified in NEC Table 250.66. The size of the grounding electrode conductor is based on the size of the service entrance conductors. It is also important to ensure that all connections are made properly and are tight to ensure a low impedance path for fault current. In addition to bonding the neutral and ground at the service equipment, it is also important to bond all metal enclosures and equipment to the grounding system. This includes metal conduits, junction boxes, and equipment housings. Bonding these metal parts ensures that they are at the same potential as ground, which reduces the risk of electrical shock. The equipment grounding conductor (EG) is used to bond these metal parts to the grounding system. The EGC is typically a green insulated wire that runs with the circuit conductors. It is connected to the metal enclosure of the equipment and then to the grounding busbar in the panel board. The size of the EGC is based on the size of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. Proper grounding and bonding are essential for the safety and reliability of electrical systems. It is important to understand the requirements of the NEC and to follow them carefully. Failure to properly ground and bond an electrical system can result in electrical shock, fire hazards, and equipment damage. In the specific scenario of a 480 volt to 120/240 volt delta-wye transformer, the neutral and ground must be bonded in the 120/240 volt panel. This is required by the NEC and is essential for safety and proper system operation. Here's a breakdown of the key considerations. Firstly, identify the transformer type as delta-wye. Secondly, locate the neutral connection on the secondary Y side. Thirdly, ensure the neutral is bonded to the ground at the 120/240 volt panel, adhering to NEC section 250.24. Fourthly, use the correct size grounding electrode conductor, referencing NEC table 250.66. Fifthly, verify that all metal enclosures are bonded using the equipment grounding conductor, referencing NEC table 250.122. Ignoring these requirements poses significant safety risks. For instance, a floating neutral can lead to unpredictable voltage levels, potentially damaging sensitive electronic equipment. Furthermore, an inadequate ground connection can increase the risk of electrical shock during a fault condition. Always consult with a qualified electrician to ensure compliance with all applicable codes and standards. Remember that electrical work can be dangerous, and it is always best to leave it to the professionals. In summary, the bonding of the neutral and ground in the 120/240 volt panel of a 480 volt to 120/240 volt delta-wye transformer is not just a recommendation, it is a mandatory safety requirement dictated by the NEC. This bond ensures a low impedance path for fault current, prevents the neutral from floating, provides a stable voltage reference, and ultimately protects people and equipment from electrical hazards. Always prioritize safety and consult with qualified professionals when working with electrical systems. Furthermore, consider the implications for different grounding schemes such as separately derived systems and the impact on ground fault protection. Understanding the specific requirements for each scenario is crucial for maintaining a safe and reliable electrical installation. Always verify the local codes and regulations, as they may have specific requirements that differ from the NEC. It is also important to consider the impact of harmonics on the grounding system. Harmonics are non-sinusoidal currents and voltages that can be generated by electronic equipment. These harmonics can cause problems in the grounding system, such as overheating of conductors and equipment. To mitigate the effects of harmonics, it is important to use properly sized grounding conductors and to install harmonic filters. Another important consideration is the type of grounding electrode system that is used. The NEC recognizes several different types of grounding electrodes, including ground rods, ground rings, and metal water pipes. The type of grounding electrode that is used will depend on the soil conditions and the availability of suitable electrodes. It is important to select a grounding electrode that provides a low resistance connection to the earth. The resistance of the grounding electrode should be measured periodically to ensure that it is still within acceptable limits. The NEC requires that the resistance of the grounding electrode not exceed 25 ohms. If the resistance is higher than 25 ohms, it is necessary to install additional grounding electrodes. In addition to the grounding electrode, it is also important to consider the bonding of the neutral conductor. The neutral conductor must be bonded to the grounding electrode at the service entrance. This bond ensures that the neutral conductor is at the same potential as the earth. The size of the neutral grounding conductor is based on the size of the service entrance conductors. It is important to use the correct size neutral grounding conductor to ensure that it can carry the fault current. The NEC provides specific requirements for the size of the neutral grounding conductor. It is also important to ensure that the neutral grounding conductor is properly installed and connected. The connections must be tight and corrosion-free. Loose or corroded connections can increase the resistance of the grounding system and reduce its effectiveness. In addition to the requirements for grounding and bonding, the NEC also includes requirements for ground fault protection. Ground fault protection is designed to protect people from electrical shock. It works by detecting ground faults and tripping the circuit breaker. The NEC requires ground fault protection for certain types of equipment, such as motors and transformers. The specific requirements for ground fault protection will depend on the size and type of equipment. It is important to consult the NEC to determine the specific requirements for your application. Ground fault protection can be provided by a ground fault circuit interrupter, GFCI, or a ground fault relay. A GFCI is a device that is installed in a circuit breaker or receptacle. It detects ground faults and trips the circuit breaker. A ground fault relay is a device that is used to protect larger equipment, such as motors and transformers. It detects ground faults and trips a circuit breaker or other disconnecting means. The installation and maintenance of grounding and bonding systems in ground fault protection requires specialized knowledge and skills. It is important to hire a qualified electrician to perform this work. A qualified electrician will be familiar with the requirements of the NEC and will have the necessary tools and equipment to perform the work safely and effectively. Remember to always energize the circuit before working on any electrical equipment. Use a voltage tester to verify that the circuit is energized. Wear appropriate personal protective equipment, such as gloves and safety glasses. Follow all safety precautions to prevent electrical shock and other injuries. Proper grounding and bonding are essential for the safety and reliability of electrical systems. By following the requirements of the NEC and by hiring a qualified electrician, you can ensure that your electrical system is safe and effective. Moreover, understanding the nuances of different transformer configurations, such as delta-delta or Y-Y, can further enhance the comprehension of grounding requirements. Each configuration presents unique challenges and considerations regarding neutral grounding and fault current paths. In delta-delta transformers, for example, a grounding transformer might be necessary to establish a neutral point for grounding purposes. Similarly, Y-Y transformers might require specific grounding techniques to mitigate harmonic currents. Therefore, a comprehensive understanding of transformer characteristics and their impact on grounding systems is paramount for electrical engineers and technicians. Finally, it is crucial to stay updated with the latest revisions and amendments to the NEC and other relevant standards. Electrical codes and regulations are constantly evolving to address new technologies and safety concerns. Continuous learning and professional development are essential for ensuring that electrical systems are designed, installed, and maintained in accordance with the latest best practices. This includes attending training courses, reading industry publications, and participating in professional organizations. By staying informed and engaged, electrical professionals can contribute to the ongoing improvement of electrical safety and reliability. In addition to the technical aspects of grounding and bonding, it is also important to consider the human element. The electrical safety training should be provided to all personnel who work with or around electrical equipment. This training should cover the hazards of electricity, the proper use of personal protective equipment, and the procedures for de-energizing and locking out equipment. It is also important to foster a culture of safety in the workplace. Encourage employees to report any electrical hazards that they observe and to take corrective action to eliminate those hazards. By creating a safe work environment, you can reduce the risk of electrical accidents and injuries. Remember that electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents. By working together, we can create a safer and more reliable electrical system. To delve deeper into the specifics of grounding and bonding, consider exploring resources such as the IEE Green Book, which provides comprehensive guidance on power systems grounding. Additionally, consulting with experienced electrical engineers and participating in industry forums can offer valuable insights and practical advice. The key takeaway is that grounding and bonding are not merely theoretical concepts. They are fundamental principles that underpin the safety and functionality of all electrical systems. A thorough understanding of these principles, coupled with a commitment to best practices, is essential for ensuring a safe and reliable electrical infrastructure. Always remember to prioritize safety, stay informed, and consult with qualified professionals when working with electrical systems. The consequences of neglecting these principles can be severe, ranging from equipment damage to life-threatening electrical hazards. Therefore, a proactive and diligent approach to grounding and bonding is paramount for safeguarding people and property. Lastly, consider the role of surge protection devices, SPDs, in conjunction with grounding and bonding. SPD are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. However, SPD can only be effective if they are properly grounded and bonded. The grounding and bonding system provides a low impedance path for the surge current to flow to ground, which helps to dissipate the surge energy and protect the equipment. It is important to select SPD that are appropriate for the specific application and to install them in accordance with the manufacturer's instructions and the NEC. In summary, the grounding and bonding system, along with surge protection devices, forms a comprehensive defense against electrical hazards. By understanding the principles of grounding and bonding, selecting the right equipment, and following best practices, you can create a safe and reliable electrical system that protects people and property.